Okay, then high power switching systems, otherwise known as thyristors. Okay, we really need to know two circuits. Tom?
Yeah.
You're going to turn around. We need to know two circuits. We've got to do the DC switching circuit and the AC dimming circuit. So it's two separate little subjects really that you need to know about. You need to know both circuits. The first one is the basic thyristor circuit. This circuit will only switch on a lamp or a heater. You can't switch it off again, so it's not complete. We look at the thyristor and it has a symbol similar to a diode, but it's got a gate on there as well. If we attach a switch with a resistor into the gate and press the switch, current will flow into the gate. As long as there's enough current, enough voltage there, the thyristor will switch on, current will flow through the bulb and it will latch. It stays on until you either stop the current going through here or reverse it. So either switch off the power completely or reverse it. So not a lot of use on its own because you can switch it on but you can't switch it off. We need something called the minimum gate current, IGT, very small current required to switch it on. So they're particularly useful for switching high power devices using normal everyday switches, make it much safer. They don't have any moving parts, so they're much more reliable than a relay or something like that because they don't have any arcing. When it switches, normal switches close and there'll be a spark which wears them out, so they're very efficient, long lasting. We need a minimum gate voltage of between 0.6 and 1 volt to switch it on as well. And then once it's latched on, we have something called the holding current, which is just a few milliamps. As long as that's flowing, it will stay latched until you stop that or reverse it. So how do we switch off the circuit? Well, we use something called capacitor commutation, where we add a capacitor, a second switch and a resistor. We now can switch it on using this switch and switch it off using that switch, and we need to be able to explain how that works. So here we've got an example. We need to look at the states of it and the voltages at the various points. So at first when you switched on the circuit, the load, the heater or the lamp, whatever, would be off, so the thyristor is off. One thing that confuses people somewhat is when it's off, it's when it's got 15 volts, or in this case it should be 12. But the full power supply voltage should be across the thyristor. That should really say 15 volts to match these. So therefore when it's off, all the voltage is across the thyristor, none of it is across the load, no current flows through the load. The voltage at P is going to be the 15 volts. The voltage at Q here is also connected to the power supply there. It's going to charge up the capacitor and that's going to be at 15 volts. So everything's 15, 15 and off. As soon as we close that switch, current will flow into the gate, switch on the thyristor, which will mean its resistance drops dramatically and P will get close to 0 volts. But Q will stay the same. Now we've got all the voltage across the load and the large current flowing. So all the power is dissipated in the load because it's got voltage across it and current going through it. The thyristor current is going through it, but it hasn't got much voltage across it, so it doesn't get particularly hot. And it's on. Okay? We can then release that switch. That's what this bit is here. And that means it will just stay on, it will latch on, because once we've switched it on, it will stay on, because it latches. Then, if we press this switch here, that will make this voltage here dive down to 0 volts, here. And because this side of the capacitor is dropped by 15 volts, this side of the capacitor must drop by the same amount. It's already at 0 volts, so this one actually dips right down to minus 15 volts, meaning that for a moment there's minus 15 volts here and 0 volts here, meaning this is positive and that is negative, so the thyristor is reverse biased That means the holding current stops and it unlatches. Okay? Then it goes back up to the state you started off in the beginning. So that will go from minus 15 up to plus 15. And then that will settle back down at 15 as well. And you're back to where you started. Okay? The other circuit you need to know about is the AC switching circuit. This is the one where by using an AC signal, dimming lights is inefficient using variable resistors. You get a lot of wasted heat. So this uses the AC signal to turn on the light on and off very quickly, and the amount of time it's on can be increased and reduced to make it dim or brighter. So we've got the voltage, power supply voltage. If we put a voltage, an AC voltage across a capacitor, it causes something called a phase lag, where here's the original signal, so the signal across the capacitor will be later than that and somewhat lower. If we feed that voltage then into the gate, what will happen is at the positive side of the cycle here, the gate will only switch on, or the thyristor will only switch on when the gate voltage here gets above the threshold voltage. Then it will switch on, and the load will be on for a short amount of time here until the thyristor voltage goes negative, so it's off all the time there, and then it will come on when this reaches the threshold voltage. Okay, so for looking at this one here, the voltage across the thyristor, here the voltage rises up, we've got all the voltage across the thyristor, it reaches the threshold voltage here, and the thyristor switches on. So therefore all the voltage is across the load here, BL, and then when it goes negative, all the voltage is across the thyristor again. And to change the dimming, what we do is we change the value of the variable resistor, and it effectively moves this point later and later and later and later, until eventually it never comes on at all. Okay, back like that. This is always the opposite of that. So here, there's an actual diagram somewhere. So effectively, all the diagrams, by working out the phase angle, which we'll do in a sec, you can work out whereabouts here the thyristor will come on. I'm going to do this. So for instance, if the thyristor is dimmed to about 90 degrees, it'll be like that. And the heater or the lamp will be only on for this section here. Okay.
For the minus.
Sorry?
Will not be on for the minus.
No, because the thyristor will always be off when it's negative voltage across it. So it's always off then, so you just get that bit there. And we can effectively move that one. So it's only actually ever on fully half the time. Okay? You can get something called triacs that do them both ways, so that's another number. Okay. So they move backwards and forwards. So say if it's 45 degrees phase shift, then it'd be more like here. So that would be more like that and be on a bit further. So you can move that backwards and forwards, but that always fits perfectly into that bit there. Okay, so that's voltage across the thyristor, VT, and that's voltage across the load. So you just need to learn which way around that is. Really, be clear on that. So, how do you work out the phase shift? You can see here it's forward bias there, here so it's reverse bias. Look, it shows on that. We can work out phase angle. Usually it's written like that. Inverse tan. Make sure it's in degrees, your calculator, of R over XC. We've got to remember that XC is reactance of a capacitor, which is 1 over 2 pi FC. Okay? Now to be careful there, F is always 50 because the mains frequency is 50 and they don't always give you that. 50 Hertz. So we can work out FC for the value of the capacitor. Take the value of R and do inverse tan and that gives us the phase angle. Okay? So it's just calculated bashing really and knowing what your formulas are and seeing them on there. So we've got here, we've worked it out there for this one. We've rearranged it all and put it into one, but I just do it as two separate ones, two separate little equations. It's probably easier, isn't it? 2 steps. Okay. Then we can add a diac, which just makes the switching sharper. Well, basically it means that the current won't flow here until there's enough voltage built up. These are for big high power systems, so this might be set at something like 30 volts. But because these are made more accurately than the thyristors, it means that everything will behave more predictably, and also it means that the switch on is definitely very sharp. You're just waiting for it to sharpen the switch on, adding a diac. You do need to know that little diagram. It also stops it from varying with temperature. It's like if you had a big row of lights at a theatre or something. You wouldn't want one brighter than the other. So they were slightly different, one might be brighter than the other, but they put the diac in to make it much more predictable. Okay, any questions? That's all it is really.
What does it mean by switch on? The switch on of the whole thyristor?
Switch on voltage in thyristor. Sharper. It's going to change it from being rising like that to being a suddenly coming on. So it's much more predictable when it's going to happen. That's it.